So yeah, and thank you very much for giving me the opportunity to speak here. As many of you have said already, it would have been nice to be in Vienna. I will do a hybrid. Tomorrow, I will actually follow the conference in Vienna. So, you know, one of us is there.
Are you going to, you are in Vienna right now?
Not yet. I'm going tomorrow morning. So tomorrow afternoon, I will be there. All right, so what I'm going to be talking about today is the so-called AKSZ construction interpreted in derived object geometry. And the goal of this project is to construct this as a fully extended TFT. So this is a project that has been many years in the making. And maybe the subtitle of this talk could be, or why the Cobordism hypothesis avoids a lot of work. So we will see, hopefully at the end, a glimpse of why actually trying to construct this thing in detail is kind of annoying and painful, because you want some things to commute that just don't. And you have to work quite a bit to avoid that. However, if you use the Cobordism hypothesis, the result that I'll be talking about is actually fairly easy in comparison. So what is the AKSZ construction? Let me explain the details. So there are many people in the audience who probably know this a lot better than me. So it was first, it goes back to paper by Alexandrov, Kontsevich, Schwarz, and Zabronsky. And what it is a technique for constructing action functionals, or also just simply forms or symplectic forms. And the strategy is that you what's called transgress a cocycle or a differential forms. So where do we want to get this? So we want to construct these things on sigma models. So some maps from some surface, well, some sigma to some x. So what's our sigma? Our sigma will be somehow our world volume, and our x will be our target space. And so the cocycle or differential form, you should think of as a background gauge field. So this is the thing that we want to transgress. And well, what does transgressing mean? Transgressing, if we take our sigma model maps from sigma to x, we have a nice diagram as follows. And there will be many diagrams that look similar to this that show up. This is a span. So if I take sigma cross maps sigma x, I can evaluate down to x. And on the other hand, I can just project onto the second component over there. And where is my omega, my background gauge field omega, that lives on the target. So that's something over here. And so if I have my thing on the target, I want to get something on the mapping, the whole maps. So what we do is, well, we pull back and then we try to push forward. Okay, so this is the formula that we want to interpret. So we need to have a setting where we can actually make this interpretation. So while pulling back forms, that's fine, we know how to do that. And the actual tricky part is this projection here, where we want to somehow push forward our form. And as you know, while pushing forward forms, you actually need to be able to do something like integration. So this step here will require some sort of integrating out the sigma. So we need a setup in which we can interpret this procedure. Okay, so what are some examples? Some examples, which were already in these original papers, are the A model and the B model, which are in Simon's theory, Poisson sigma model, but also the Courant sigma model. So something that uses Courant algebroids that we saw in the last talk. And of course, there has been a lot of work on AKSZ constructions and on AKSZ techniques. And I just named here a couple of people, and apologies to the many people I can't name here. If you have names you think I absolutely have to add here, please let me know. There's space, and I'm happy to add them. So our tool for today, all of these AKSZ techniques use some tools. So we said we need a setting where we can make sense of this push-pull procedure. And all of these constructions need some form of a derived geometry. So by derived geometry, I mean, this can be interpreted in different ways or implemented in different ways. There are Q manifolds, that was the original version, or then maybe a little bit more elaborate, which Rittenberg also used, the DG manifolds. And I mean, many others. Costello also has a version of derived geometry that they use for AKSZ type things. And what we will use today is derived algebraic geometry. And well, the main reason for this is that this was strongly developed and in a way where we can interpret what a differential form is. So Pantev-Toen-Vaquié-Vezzosi have this seminal paper where they explain how to define derived symplectic forms in this context. Okay, so let's look at the first example. That's maybe more of an algebraic flavor than the things that I showed you above. Of course, it's just an instance. So, and where this derived geometry comes in. So let's start with an oriented surface, closed, compact, and G a reductive algebraic group. And we want to look at the moduli space of G local systems, or G bundles with flat connections. And I mean, this is also related to what we'll see in the next talk. It's basically a character variety. So we're looking at this G local systems here, and I mean, this has been known for a very long time and goes back to Atiyah and Botts that this thing has a symplectic form. So how do we get the symplectic form? Roughly, the idea is, and we will see a little bit more about why this is the case, but why this really gives us a symplectic form. So basically what we do is if we wedge two copies of H1 of sigma, then we can pair the forms, we get into H2. Then on the second part, we can use our killing form. We have a reductive algebraic group. So we have a map from S2 of G to C. And then, well, H2 of sigma, that's just isomorphic to C. So we get a map like this. And in fact, this is actually a symplectic form. So it's not just a map. It also has a non-degeneracy condition. So let's see where the derived algebraic geometry comes in here. So this thing at the top here, you can interpret this as the smooth locus of a derived stack. And the derived stack in question will look like a sigma model. So it's maps from some derived stack I make out of my topological space, namely it's the so-called Betty stack, which just means that I just use the homotopy type of the surface and interpret this as a constant stack, derived stack. And on the other hand, I take BG as my target. So this is also a nice derived stack. And yes, so we're using a mapping stack here as well. All right, what's the next ingredient? How can we interpret this thing at the bottom as being a symplectic form? Well, symplectic forms usually identify, give a map from wedge 2 of the tangent. And indeed, if we compute the tangent to this derived stack, or just this moduli space, what you get is exactly this H1. Okay. So this here is nothing but the tangent at my local system L. All right, so I said we want to actually get to something like TFTs. We'll go to here. So what's a topological field theory? I mean, this is a program on field theory. So, I mean, I won't go into too many details here. You probably have all seen an instance of this. So topological field theory, classically, following Atiyah and Siegel, is, in modern language, a symmetric monoidal functor out of a category, which I will call board in this talk. Sometimes it's called NCOB, where the objects are n-1 dimensional closed manifolds, and my morphisms are n-dimensional cobordisms. And usually our target will be something like vector spaces. That's for topological quantum field theory. Usually we take vector spaces here. So what does fully extending now mean? I have something I have to uncover here. Right, so this will be a symmetric monodal functor of categories. And so the main somehow point now will be, well, we want to extend. So what that means is that we don't only want n-dimensional and n-1 dimensional things on the left-hand side, but we also want higher codimensional things. So maybe n-2, maybe n-3, and so on. But then the language saying we have a symmetric monodal functor of categories is not the right language anymore to encode this. Okay, so extended means that we want to get some sort of a higher category. And for the purposes of this talk, I won't go into details of what I mean here. It will only very briefly be mentioned later on. And so usually the way we depict this is now, for example, here, if we have a three-dimensional situation, we might have as objects points, as morphisms, such things here. So this would go, this would be my source, 3 points, and my target would be just 1 point. What about the next one? So the next one will be a two-morphism. It will be a morphism between morphisms. So this should also have a source and a target, and my source will be here in the front. And my target, which color can I take? Maybe purple, will be here in the back, the two lines here in the back. So this is how we see this funny open pair of pants, or riding chaps, as somebody might call them, as a two-morphism. Or then we have a three-dimensional situation. This you should think of being a cylinder with a pair of pants cut out. So this is actually a three-dimensional thing, which goes from the cylinder to the outside to the pair of pants in the inside, or vice versa. I haven't actually specified it here. And so a big part of somehow dealing with fully extended topological field theories is, well, before it was rather clear what to put on the right-hand side. We just put vector spaces. But now it's not at all clear what to put on the right-hand side. We need to find a good replacement of our vect and linear maps. And here I just wrote some that we sometimes consider, and I think will probably appear in the next talk. But this will not be the flavor of topological field theory that I'm talking about today. So these have always the flavor of being somehow, I mean, we always have some sort of vector spaces floating around. I mean, we have bimodules would also be some sort of vector spaces with extra stuff and so on. But this is not the type of situation we'll be looking at today. Today, we'll be looking at what we could call semi-classical topological field theories. So we will see a different type of target arising here. One last thing I would like to mention is that we don't just have an n category going from object morphisms up to n morphisms, but actually we will look at infinity n categories. So these actually include having a moduli of Cobordisms, some sort of a, at the top, we don't just have, so for example, in this case here, we don't just have our top dimensional Cobordisms, but we actually have the full information about the moduli space of these Cobordisms. Okay. All right, so I said that this type of situation, which would all be some sort of quantum, maybe I should add this here. These are somehow quantum type targets because we have something linear. We have something like vector spaces and souped-up versions of vector spaces. But now the AKSZ construction that we will talk about today won't be that flavor, but rather it will be something like a semi-classical thing. And I will explain now what I mean by this. So we saw above that if we take sigma, a closed surface, then we get a symplectic structure on our mapping stack. But now, I mean, we want to get to Cobordisms, so we want to have things with boundaries. So what happens if I now take a manifold, a three manifold with a boundary? So the boundary will be some closed surface. There I know I get something symplectic. But what about my manifold? So what I can do here now is I can look at G-local systems, which extends to all of the manifold. So this is the thing that we looked at before. G-local systems on a surface. And now we're looking at those G-local systems on the surface which extend to the bulk of the manifold. Okay, so here again we have a nice diagram which actually will show that this inclusion is Lagrangian. So before we had a symplectic thing, and now actually we have a sub thing of a symplectic thing, and this is actually Lagrangian. Again, this has been known for a long time. And basically you can look at this diagram and this shows why this is, well, isotropic, but then there's also non-degeneracy that you can see. And of course, as you can probably guess, this has to do with Stokes' theorem. So before we were looking at this map here, and that was the symplectic form. And now we have to see that if we restrict it to the tangent of the manifold, we actually get 0. And that's true exactly because of Stokes' theorem. Okay, so again, we have the tangent spaces, and we have a map between the tangent spaces. Okay, so one thing to notice is I won't really tell you much today about what derived algebraic geometry is, but in this situation, you can really, I mean, you can always take a tangent, which will actually be a tangent complex. So it will be somehow an enhancement of this situation here. It won't just be the H1, it will be the full complex that's behind it. And in fact, then the same situation holds. And again, it's just Stokes' theorem. So that will be somehow the upshot here. Okay. Are there any questions so far? All right, so let's go back to the Cobordisms. It's a lot faster to give a talk if you don't have to write. So I hope I'm not rushing through this too much. So, right, so what do we do? What does this TFT do for you? So let's start just with a simple situation of one Cobordism. And so our setup will be, well, our Cobordism actually gives us something that appeared before, namely a Lagrangian correspondence. So, sorry, a Lagrangian. So now we just had a single boundary. We were only looking at one boundary. But now if I decompose my boundary into two parts, as I would do in a Cobordism, I get a map from the G-local systems on M to the product of G-local systems on one part of the boundary times the local systems on the other part of the boundary. So what I really have is, if now X, in the previous case, X was just BG. That's something that we saw way further up. But now I can actually take X to be any derived stack. And this derived stack will be what's called N symplectic. Okay. And so now my inclusion here, what am I doing over here? I'm actually including my in boundary into M. And I'm also including my out boundary into M. And so I can now apply maps blank, comma, X. And actually, I mean, to fit into the framework, I want the steady stack, but to get a diagram where the maps go the other way. So I get a span. And the fact is, the analog of what we had before is that the span here is actually a Lagrangian correspondence.
Claudia, just a short question. So when you say it's a Lagrangian correspondence, so you're already assuming that we understand that the space on the top is kind of symplectic, right?
This X is symplectic, yes.
Yeah, X is symplectic, but we need now map MBX.
Well, MB, yeah, well, right. So we can use, did I not? Right, I guess I did not mention this before.
In the beginning, you said it will be symplectic, and now you gave an example where it is symplectic. Do I understand correctly? Now we kind of jump the gap and we assume.
Right, so there are several parts of the statement. So first part is that this here is symplectic, as you said, and now I have to get the dimensions right. N minus D minus 1 symplectic. So if this is D-dimensional and this is D minus 1 dimensional, the boundaries, then the PTVV, the seminal paper, showed that in fact, here, we can use this transgression that we saw above, and you get that this here is symplectic, where we shift by the dimension of this first part here, exactly. So part of the statement that this is a Lagrangian correspondence includes that these bottom parts here are now symplectic with a certain shift, and that this correspondence here is Lagrangian. Does that answer your question?
Yes, thank you.
Absolutely. Okay. Right, so what does Lagrangian correspondence mean? Just to be clear, we have, having these two maps implies that we have a map to the product where I reverse the symplectic structure in one of them, and that this map should be Lagrangian. Okay, so what Damien Calaque showed actually is even more. He actually showed that this procedure gives you an oriented d-dimensional topological field theory. So what I guess I didn't write here, I wrote it above, but this should be oriented. We're using Stokes' theorem here several times. So of course, this involves having a good category of Lagrangian correspondences here. And I will explain this a little bit on the next slide. And I hope I have the space. So what the goal of this talk is to explain to you, or to convince you, that we don't just have an ordinary TFT here, but we actually have one of these fully extended TFTs. Okay. So what is my target? I will explain a little bit more about this. I realize I should have left more space here to explain this. The ingredient for the fully extended situation is we need to have a replacement of the target. We need a generalization of this, where objects are symplectic, shifted symplectic manifolds, stacks, and morphisms are Lagrangian correspondences. And so we need a higher category thereof. And so by higher, what I mean, well, there was an infinity 1 version by Rune Haugseng, which we immediately built upon. There was also 2-category version by Amarim Ben-Bassett. And there's also actually a Poisson stack version, so for n Poisson instead of n symplectic, by Haugseng, Melami, and Safronov. And so let me explain to you a little bit what these things are. So objects are n symplectic stacks. So I haven't actually told you what an n symplectic stack is, but the important ingredient will be that we have a tangent or a cotangent complex, the whole chain complex instead of just a space. So this is, this is similar to things that you're probably used to from other derived situations, but you definitely have a complex there. Okay, so what's a Lagrangian correspondence? A Lagrangian correspondence, well, it's a diagram like this. So if we look at the tangent complex, we actually get a diagram of the tangent complexes. This is something that should be familiar to you. If you have a tangent space, well, then, a tangent vector, well, then, yeah, you can pull it back. But now what we can use is X and Y are assumed to be symplectic. Oh, that was wrong. And symplectic, actually. So that means that I get that my tangent will be quasi-isomorphic to the cotangent. I guess I erased too much here. I should have left a little bit more. So forget the bottom half of this for the moment, but that means this middle part here uses that X and Y are symplectic. So here I can explain to you a little bit of what symplectic is supposed to mean. Usually symplectic means you have an identification of the tangent and the cotangent space. Well, now we have complexes, so we ask for an identification of the tangent complex and the cotangent complex. But since we have chain complexes, that might involve a shift. So I might be able to shift my tangent complex a little bit and then identify them. So we have a quasi-isomorphism here. Okay, and so the remaining part of being a Lagrangian correspondence, if you just look at this bottom half here, well, this looks very much like this top half dualized, and that's exactly what it is. So we now have here a square of complexes, of chain complexes, and the condition for being a Lagrangian correspondence is that this is a homotopy pullback or pushout. Okay, so that's what it means to be Lagrangian. So what's composition in this situation? So composition, if I now have two such Lagrangians, will be, well, we simply take the homotopy pullback. So, I'm running out of space again. So this is the nice feature here, that actually this exists and gives a Lagrangian correspondence. So this was part of what Damien proved. This will be the composition of the Lagrangians L and L prime. So that's really where the derived comes in. So usually you can't do that. Think of the usual situation if you have two Lagrangians in a symplectic manifold. If you want to intersect them, you can, and you can only do that if they're transverse, and then you get a Lagrangian again, but you need this transversality. And that's somehow the slogan of the derived geometry. It fixes problems with transversality. So that's why this framework is useful here.
Could I ask a question? This is Edra here. Just about the technical details of the composition.
Sure.
So clearly there's no canonical choice, which is exactly why we're doing higher category theory. But in this context, should I be thinking infinity one?
Yes. So what I'm explaining right now is an infinity one category.
Mm-hmm.
And then of course you can take its homotopy category. So that's what Damien actually did. That's part of the statement here.
I'd rather not do that.
Well,
but I should think in terms of it is actually an infinity one category, not something
an
worse.
infinity one category, yes, absolutely.
All right, thanks.
So that's this infinity one category that Damien, Rune defined in full gory details. And Damien in his paper defined the homotopy category right away.
Oh, I'm sorry. Your yeah, my question was answered on your slide. Okay.
That's fine. That's okay. Okay, so now, right, so now we more or less understand what this infinity one category should be. And now I want to give you an idea of what to do to get two morphisms. So now we want morphisms between such guys. That will be the next step. So what's a two morphism? A two morphism looks as follows. We have a one morphism here. That will be our source. Okay, so maybe I should see if that works well. This is our source. And then we have another one, just this guy over there, and that will be our target. The Lagrangian correspondence is somehow given by this curly L up here. And so now let's repeat what we did up there. We first take our diagram and we hit it with the tangent. We take the diagram of the tangent complexes. So this diagram looks exactly the same. I just added a T in front of everything. And I started omitting these maps here. I just don't want to include them in the notation, but of course they're there. So now we're at the bottom here. And so my bottom guy, if you look what we have here, we added now the n symplectic form. So we have to do that again. Our x and y have to be n symplectic. Well, they're objects, so they are. That's good. And now at the bottom, we flip the diagram upside down and we get a big diagram. And so our condition is that this is a homotopy. I don't know what my abbreviation is here. Homotopy limit diagram. So that's the analogous situation to before. So where does the shape come from? This might look a bit arbitrary for you right now. So let me rephrase the shape. This up here, this shape. So why did we guess the shape? Well, the shape comes from, if I unpack this a little bit, it looks as follows. Well, I can put my x and my y on the sides, and it looks like this. And so what I would like you to notice is that, well, a two-morphism, the picture that you should always have in mind for a two-morphism is you have a source and a target, and then some two arrow in between. Well, here we have our source, one morphism. This is just a Lagrangian correspondence, and this is a Lagrangian correspondence, and then this is our two morphism in between. So that's where this shape comes from. But now maybe let's connect this to Cobordisms, or why we could expect shapes of this form to be the outcome of a topological field theory. Well, let's look at the two-Cobordism that I had before. This was the shape. I explained to you before that the source were these two half circles in the front. So this is my source, or maybe I switched the direction now, but it doesn't really matter. My target are these back guys, so that's my M. And so the diagram that I get, I can just look at the inclusions. So the sigma is now the source of this front thing. Those are these 2 points, or equivalently these 2 points in the back. But if you notice, those are the same. So where this comes from is now I can actually look at sigma included into M or included into M prime, or sigma prime included into M or in M prime. And then both of those are included into the big guy, N. So this is really just the geometry of what's happening on this side. So we get a diagram like that. And if you compare this diagram at the top to that diagram down here, well, the arrows just go the other way. Apart from that, they're exactly the same. Okay, so that means that if we hit this bottom diagram, oh, now I erased something. If I hit the bottom diagram, maybe let's make this in red because this is important, with maps from this thing, or I mean, I want to be in stacks, so I have to do my Betty thing, into the constant target X, I will get a diagram like the one above. And now the claim is we want to get something like this. And the claim is that this comes from taking the orientations on this side. That's what we used before. We were integrating somewhere. We were doing Stokes' theorem. So you integrate here. We use our orientations here on sigma M and so on, which are induced from N. And we use that this guy is symplectic, the X. And with that, we will see that all the components in the diagram we get from putting maps here everywhere will be exactly that. So what's now our strategy for fully extending the TFT? So the first strategy when fully extending a TFT, I want to claim that the first strategy that you should have should be actually this first one, namely use the Cobordism hypothesis. So I won't repeat what the Cobordism hypothesis is. I hope many of you have seen this. It says that any fully extended TFT is given by its value at a point, and I can actually characterize the values that this can take. So we can get these fully extended TFTs by showing that any n symplectic stack, so that will be my x. So this should be my x, my target, is dedualizable. So I want to get a DTFT. I didn't write this here, and it should be oriented. It should be dedualizable and oriented. I don't want to explain what that means, but there's a part of the Cobordism hypothesis which tells you how to get that. And actually, this is a relatively easy thing to do. So I haven't told you what dualizability is. Those of you who were in my talk 2 weeks ago saw me explain this in a different context, in a different target category. But this is actually a relatively easy thing. So basically what you do is the dual of a symplectic stack is take the same symplectic stack, but with its opposite symplectic structure. And the adjoint of a correspondence, well, that's just an L with maps to X and Y. But I can also view the same thing as a correspondence from Y to X. The only subtlety is that because we don't just have a correspondence, but a Lagrangian correspondence, we have to kind of switch the structure here a little bit, but that's all we have to do. So, I mean, getting the duals and showing this is actually is not very difficult. So, right. So to show that a Lagrangian correspondence is dedualizable, that's not that much work. It basically it's a good exercise to try to show this type of situation, not for Lagrangian correspondences, but just for correspondences. And if you work through the definition of dualizable, this is something, I mean, one can give as an exercise for, say, PhD students. This has nothing to do with derived algebraic geometry. This is quite easy. On the other hand, and our actual goal for this project was to really give an explicit construction. So we know what this thing should be. The problem about the Cobordism hypothesis is it gives you a very nice tool to actually construct a fully extended TFT, but it's not that easy to know what it evaluates to then on certain Cobordisms. But here, I mean, what we've been doing the whole time is, well, we believe that this should just be given by these mapping stacks. So we should be able to just write this down as it is. So our goal was actually really to construct a symmetric modular functor of infinity n categories. And so what does that mean? Well, in fact, what this means is we construct it as a map of n-fold Siegel spaces. And then we also have to deal with a symmetric monoidal structure. And in particular, this should be a map of n-fold simplicial spaces. At least we would like, I mean, not every functor of infinity n categories arises this way, but I mean, we would like to have it just as a map of n-fold simplicial spaces. This is something, you know, we're reducing our complexity. Now we just have, I mean, n-fold simplicial spaces are something we understand very well. But the problem is that if we define it that way, if we want a map of simplicial spaces, diagrams should actually commute. Maps between simplicial spaces are commuting diagrams. And the problem is that in this situation that we're in, the diagrams only commute up to homotopy and not strictly. So the hard work of this project has been to actually find a way to strictify things. And I would just like to illustrate this with a very small example without telling you details of why, but just that you see that somehow where things go wrong in some sense. So one example is that if we look at the orientation of M as a map from sigma to sigma prime, well, this orientation, the part of the orientation that we actually need amounts to just integrating forms. I mean, this is something that we've seen throughout the talk. We were just using Stokes' theorem over and over. And so in PTVV, the way this is encoded essentially, I mean, is by a map to K. Maybe with a shift that corresponds, the shift corresponds to the dimension. So here D minus 1. Okay, so let's look at the following diagram. So we want to just, our orientation corresponds to integration. That's what I said. So we integrate a form on sigma, and we land in K shifted by minus D minus 1. Or we integrate a form on sigma prime, and we land in the same thing. Or we could integrate in the middle with M, then we would land in actually in K shifted by D. So there's already something weird going on here. But okay, I mean, that's actually the interesting part lands in K, yeah, it lands in K shifted by D, which means that if I can map it to here, then it's 0. So where we see this stuff encoded in a better way is if instead we actually make this diagram. I could have just put this here, here, and here and written equality everywhere. But actually, we want to replace this middle part of the diagram by a bigger chain complex. So this chain complex in the middle now will be quasi-isomorphic to just the constant guy in degree D minus 1. But now we actually encode all the parts. And so now we actually get a nice commuting diagram which fits together. Whereas before, I mean, well, if you go over here and restrict and you go over there and restrict, I mean, these are obviously not equal, but they will be equivalent because their difference is governed by a form of higher dimension or by the integration over M instead. So this is the type of thing that you have to do in this situation. You have to replace, in this case, this constant diagram by something that's a little bit bigger. It's quasi-isomorphic here to just putting K in degree D minus 1, but you have to deal with these things. So that's the type of situation that appears. Because in these fully extended TFTs, you always have to keep track of all these pieces of information. So they should be there somehow. All right, so let me finish by some final remarks about this construction. So first of all, this construction is, in quotation marks, adaptable to other derived geometry setups. So, I mean, the things that we use, the tools that we use are relatively general, as long as you have a good theory of derived geometry. I mean, this is a bold statement, and I should probably not state it that boldly. But as soon as you have a situation where you can interpret differential forms, and you have good pullbacks, and you have good intersections, and so on, then you will be able to do this construction. So you need to be able to interpret what a manifold is. So that was, in our case, the Betty stack. Just remember the homotopy type. But apart from that, I mean, the method should be adaptable. Also, it should generalize to Poisson stacks. So those three authors before, Haugseng, Melani, Safonov, they generalized the targets actually to a Poisson version of that. And there are also these AKSZ versions for Poisson stacks. Then I should remind you of Natalie's rule: don't define infinity cats, or in our case, their functors, from scratch, since it's hard to get coherences, right? So I hope I wanted to illustrate that a little bit and where things might go wrong. And then the last point I would like to make is that the Cobordism hypothesis simplifies our lives. So we might not be able to then know what it does explicitly on all things, but it's often a lot easier to construct fully extended TFTs. All right, thank you very much.
Thank you very much for your talk. Any questions or long questions?
Yeah, I have a question. Can you hear me?
Yes.
I mean, you probably know what I'm going to ask, but does that get you any closer to prove some statement along the line of that factorization homology quantized mapping stacks?
No. Unfortunately, no.
Okay.
Not at all. I mean, with quantization, that would be a dream in some sense to get a quantization as well. I mean, in some sense, we have now, right? We have board M or oriented, but and now we have this lag, and then we have the one that you want with a factorization homology. And so, you know, the dream would be to have a map like this, right? Which would be quantization.
Yeah.
But that doesn't work in general, actually. So actually, there's a linear version of this. Linear version, BD quantization by William and Haugseng. But this really only works in a linear setting.
I see.
Where the stacks are just linear.
I have a somewhat more naive question. So the AKSZ construction from the very beginning, it was a tool to build sigma models, right? Meaning some kind of action functionals, and then out of them maybe producing Euler Lagrange equations. So now naively fully extended would mean that you have manifolds with corners, and you have contributions to some action functionals in different codimensions of the boundary. And so can one translate what you're doing to closer to that language, or what kind of does it have some meaning in more like sigma model, back to the sigma model language?
So I mean, basically there is I have them up here somewhere. So there's a work I'm sure you know of Catanion, Nyof, and Reshetikin, who basically do something along those lines. So I have actually tried to understand how to get theirs from a situation like this. But of course, here we are really using derived algebraic geometry and not derived differential geometry. So one would need, that's also why I said at the very end, like it should be adaptable as soon as we have a good theory, consistent theory of derived smooth stacks. And of course, there are many things that go in that direction. Many people have been working on this, but I don't know at this point, at this moment, how to translate it. But if you look, I mean, the forms that they get on the boundaries and so on, I mean, that looks very much like these push forwards that are happening in our situation. But at the moment, I don't have the skill, the tools to actually translate precisely.
So even not in some toy situations, right?
I have tried in toy situations, I have to say.
Okay. Thank you.
But that's something one should try. I fully agree. Yeah.
I have a question, Claudia.
Mm-hmm.
So at some point in your talk, you said that there's a sort of two ways you can go. Either you just invoke the Cobordism hypothesis, or you just try to do things explicitly. And then you decided to do things explicitly just at the level of a functor, not at the level of a symmetric monoidal functor. Is that correct?
No, actually we get a symmetric monoidal functor. I just haven't been explaining that.
Oh, I see. Okay.
Yes. No, we have a symmetric monoidal functor, absolutely.
Okay, cool.
So, I mean, that part is actually relatively easy because, I mean, take disjoint unions and that translates to products. So that's actually the easy part.
Well, okay, good.
Here, symmetric monoidal functor.
So,
Okay, then
Claudia, sorry, can you say again, maybe summarize what the input data of the construction is?
So the input data is this n symplectic stack, which is the target. And then, so let me add this here. Given x, it's the same n symplectic stack as before, construct the symmetric monodal functor, and this is given by maps out of whatever Cobordism you have with target x.
So from what you said before, I had the impression that there is also a kind of form omega on this stack. Where is this now?
On x, yes. So x is n symplectic. And
Okay, it's in there. I see. Okay.
Where of course we have to interpret form in this setting of derived algebraic geometry.
So at the beginning, you had the example of taking just BG, where you said G is algebraic group.
That's a great question. So yes, so BG is actually a two-symplectic. BG is a two-symplectic stack. And this comes from the killing form. So the killing form is a map from a pairing, symmetric pairing on G with non-degeneracy. And in particular, if you wish, it gives you a map like, sorry. Maybe I'll show you the exercise afterwards, but the point that I want to make is that you get this two because this killing form is actually symmetric on G, but then if I add a shift, it becomes alternating. And so it will actually give you an alternating thing on G shifted by 1, and G shifted by 1 is exactly the tangent of BG at a point.
I'm a bit confused with this too, because usually when somebody considers sigma model with like target space BG, then this should be something like Schoen-Simon theory, where I would expect maybe a 3 or 4 form, something.
So, well, on BG we have the 2, but if we go back and look, where was it? Here in our example, here we had the 3 manifold. Right, so on the boundary is a 2 manifold. There we get a 2 minus 2. So 2 was the BG, the 2 of the BG. And then this is 2-dimensional. So we get a 2 minus 2 equals 0 symplectic form. Whereas on here, if we do the same type of transgression, we would get a, something weird. But that's where this comes from. We get this actual symplectic form here.
I see, okay.
May I ask a question?
Sure.
Yeah, Joe Wittenberg over here. Yes, so do I understand correctly your scheme being so you're given a shifted symplectic stack on the target, so you use that to build a higher category of Lagrangian correspondences, and then you transgress everything, using this, pull back, push forward over manifolds of various dimensions.
Yes.
Is that a correct interpretation?
Absolutely.
Okay, so let me try to see, well, if I can understand it in a well-known example, like a Poisson sigma model, right? So there you have a one-shifted symplectic structure on the target, right? So it's symplectically algebraic. And so I guess the Lagrangian submanifolds there correspond to
quasi-tropic submanifolds of the the Poisson manifold. Right? So that's where they create the boundary conditions for for the sigma model, for the Poisson sigma model. So there's only one layer left in that case. So what corresponds to the points in that in that example? Like where do the points go?
So the points will always be sent to the shifted symplectic stack that's your target. So you started with, what did you say, a one shifted tangent thing?
Yes, the one shifted cotangent bundle of a Poisson manifold, right?
So
that's one shifted symplectic.
Yes, so a point will go to that one. So the thing that you assign to the point is just maps from point to X. So that's just X itself.
Okay, and then let's see. So what happens then? I'll try to see if I can get this. So I have 2 points, let's say, a line segment between them, right? So this open line segment, I guess it's somehow supposed to go to what something quasi-tropic inside your Poisson manifold, like.
Yeah, so this should be the trivial thing. So it should roughly be something like X viewed as the diagonal in X cross X bar, I guess, to get the.
Yeah, something like the graph of the identity map or something.
The graph of the identity map, exactly.
Oh, I see. So that's quite yeah, that's of course quasi-tropic in the product, Lagrangian rather. Okay, thanks. I need to think more about this, obviously, but thanks for a very interesting talk.